Hello, in this lesson we're going to be talking about related rates. So these are things where obviously different rates that are related to each other, such as, for example, the rate at which I'm dumping water into a vessel and the rate at which the height of it is filling up. So if you can imagine the room that I'm standing in being filled with water in a flood, we'd want to know the rate at which obviously the water comes into the room. We'd have to take into account the dimensions of the room and then see how fast the water line would go up. So anyway, there's all kinds of course, applications of different rates that are related to each other. The first one, again, if you go to this PDF that I posted right above the video, first of all, I give you kind of a framework there, the first 6 steps. The first one is to draw a picture. Second one is to write equations using the given information. The third one, write an equation containing all the variables of interest. The fourth step is to differentiate each side implicitly. The fifth step is substitute in everything you know from the given information. And then the last one is to solve for the rate of change. The basic idea is this. We need to take into account the information that's given to us, come up with some equation that unites all of those things, and then of course take derivatives because rates of change are derivatives. The first problem is the ripples in a pond. The problem says a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So just imagine, the pebble goes in here, so we're dropping straight into the wall here, and then you're getting concentric circle rings, concentric circular rings, heading out, and these would of course be expanding more and more. The radius of the outermost ripple is increasing at a constant rate of 1 foot per second. So here's what I mean by my step 2 in there is writing equations using given information. If the radius is increasing, I'm thinking the rate of change of the radius, rate at which the radius changes with respect to time, is increasing at 1 foot per second. I've left that as positive because it's increasing. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? You'll notice that I did not immediately write r equals 4. Reason for that is we can't just say the radius is 4. If you imagine the ripples increasing, the radius is only 4 at one instant. Okay? So I wrote this down because we're told that's the rate at which the radius is increasing, which tells me that that's the way it's increasing the whole time. As opposed to the radius being 4, clearly we know that's one instant when this radius is 4 from here to the outermost ripple. So we can't say like, oh, r equals 4 feet. We'll use that, but only when we're ready. So then we have to come up with, the question says what rate is the total area of the disturbed water changing? We need a formula that unites area with whatever else we know. And the only other thing we're given information about is the radius. So our area formula is pi r squared. So in our framework, I'm on step 3, writing an equation that relates everything together. The fourth step is to differentiate each side implicitly with respect to time, in this case. So dA dt, again, pretend area is some function of time that you don't know, because we actually don't know it already. It's based on the radius. So dA dt is 2 pi r dr dt. And if you're wondering about that, remember that pi is a constant, right? 2 pi times r to the first. And again, radius is also dependent on time. We know radius is dependent on time because we're told so right here. So dA dt is what we're trying to find. It said at what rate is the area of the disturbed water changing. So we have 2 pi. Well, at this point, we're prepared to substitute the radius value in, which is 4 feet. Let me check that, make sure it's 4 feet. Yeah, when the radius is 4 feet. The reason we can substitute it in there is because at that instant, how fast is the radius increasing? Had I substituted it in here, your area would have been pi times 4 squared, which is 16 pi. The derivative would be 0, which would be implying that the area isn't even changing, which of course it is. And then I've left off my dr dt, which is 1 foot per second. Notice I'm keeping my units here. It's a really good idea for a couple of reasons. One is, the units are obviously important in the context of the problem. And two is it makes sure that you've done things properly. In this case, for example, I'll have feet times feet per second. That's square feet per second. And it should be that way because it's an area. So you get dAdt is equal to, looks like 8 pi square feet per second. So that means as this pond ripples out, it'll be occupying every, at that instant, it'll be heading out at 8 pi meter, I'm sorry, 8 pi square feet per second. Okay, another question, which is a pretty classic example, is a ladder on a wall. So we're told, you've got a wall and a floor here, and you've got your ladder. So there's my ladder, right? It's up against a wall. If the bottom of the ladder slides away at a rate of 0.5 meter per second, so we need a distance for this, I'll call it x. How fast is the top of the ladder sliding down the wall? So I'm going to call that thing h as in height. You could easily call it y or whatever you want. How fast is it sliding down the wall when the bottom of the ladder is 4 meters from the wall? Okay, so I didn't label this as a variable because that thing is not variable, it's a ladder, and we're told that it's 6 feet. So what I'm going to do is set up a Pythagorean identity. X squared plus h squared equals 36. That's going to be my equation that unites all the information. Yeah, if you just throw it over there. Thank you. Sorry.
Sorry.
No, it's all right. So now I'm taking, I found, this is just based on the fact that I know it's a vertical wall. Sorry about that, just someone can drop something off. This Pythagorean theorem, and this just came, it wasn't given to me in the problem, in the question. That's really where you have to have the, not necessarily stroke of genius, but you have to have the original thought of, oh, I'll use the Pythagorean theorem because it unites all of my given information. Now we will take the derivative, 2x dx dt, 2h dh dt is equal to 0. So we're told a few things. The bottom of the ladder slides away at 0.5 meter per second. That's dx dt. And notice it's positive because x is increasing. If you imagine this triangle, the bottom will be sliding out and the top will slide down. And we're also told top ladder, when the bottom is 4 meters from the wall. So at that instant, x is 4 meters. dx dt is 0.5 meter per second. H we don't know yet. We do know dh dt. I'm sorry, we're looking for dh dt, my fault. And now the question is, how do we find x? Well, I'm sorry, h. Well, we know that x is 4 at that instant, and we know that this is 6. So you can do your Pythagorean theorem calculation to find h. It'll be 4 squared plus h squared equals 6 squared, so that's 16 plus h squared equals 36. So I get root 20. I put feet there, but I should have put meters. So check my calculation there. And now all you'll do is a bunch of algebra and solve for dh dt. You'll notice that you'll move over square meters per second, you'll divide by meters, and I'll just leave that for the viewer to do. And the last question is a person walking underneath a lamp post. By the way, the last two problems, the first one is very simple. Pi r squared, area equals pi r squared. This one you kind of had to come up with a new thing here. And this next problem, the person walks away from the lamppost. They are 6 feet tall. So let me label him as 6, or her as 6. And they walk away at a rate of 5 meters per second from a light post, and this is our light post that's supposed to be in the same ground. And this thing is 15 feet tall. Suppose the person is 10 feet from the post, and find this stuff here. So the first thing is what rate is the tip of the shadow moving, and what rate is the length of the shadow changing. So the tip of the shadow would be the tip of the shadow is the black dot on the end there. Now the length of his shadow is not the same thing, because the length of his shadow only occupies this much space, versus the tip of his shadow goes from the lamppost all the way out. So one will, obviously they're quite dependent on each other, but we need to find a way to relate these things. So maybe call his shadow, it doesn't really matter, how about S? So I'm making my S look a little funny, so it's got two little guys on it, so it doesn't look like a 5. And maybe call this X, his distance from the pole. So now we need to come up with a way to relate all of this information, and we're told also at a certain instant X is 10, given that he's 10 meters from the wall. So let's then come up with something. You might want to hit pause here, come up with some idea that relates 15 and the X and the 6 and the S, and come up with some way to relate them. Okay. The way that I'm going to relate these things is actually a simple idea from geometry, just similar triangles. So we're going to take the larger triangle, which I'll indicate to you how they're similar here in a second. We know those are both right angles, the two black angles that I put in there. And we also know in both triangles, in the whole triangle versus the smaller triangle, they both have that angle, and they both have a right angle. So by your geometry facts, you have angle-angle similarity here. So we can set up a similar triangle situation. We could have 15 over 6 is equal to, see if you can complete the thought for yourself. Want to relate this and this, so it'll be X plus S over S. And even here, before we take the derivative, we can simplify that significantly. It'll be 15s equals 6x plus 6s. When we subtract the s's over, we get 9s equals 6x. And that's actually fine for me. If you wanted to reduce it, you could divide everything by 3. I guess I'll do that. It doesn't matter. Point being, from here we can take the derivative. So on the left side it'll be 3 ds dt equals, oh, I'm sorry, I didn't reduce the 6, equals 2 dx dt. We're told that dx dt is, he walks away 5 feet per second, so that's 5 feet per second, and then you can solve for ds dt. So this one is 5 feet per second, and then you'd be able to solve for ds dt. Interestingly, something to note here is that there are no variables left when we take the derivative other than the rates of change. So in this particular question about, for example, to find ds dt, how fast is the shadow, just the length of the shadow changing, it's not dependent on where the person is. That the rate of change of the length of the shadow is going to be only dependent on how fast they're walking, not on where they are. If you solve for, if you want to know the rate at which the tip of the shadow is changing, you can take ds dt and dx dt and add them together, because dx dt will be the space between the person and the post, ds dt will be the length of the shadow, so the tip of the shadow is all the way out at the end of those two things added together. So this is just a few ideas of what related rates can be like. Here we've got a Pythagorean theorem, here we have a simple similar triangle. All kinds of different things can come up from this. So you can obviously have a chance to make all kinds of calculations and lots of practice on this after the video. Thank you.